Now, the next problem is a classical problem. It's called the diamond-shaped airfoil, diamond-shaped wedge airfoil. It really just depends what you would call it. So here's what it looks like. So at its basic, I have a diamond. And this diamond is, for some strange reason, flying at supersonic speeds. Woo! It's fast. My goodness. Now we have to give it some values here. So first off, we need to realize it's supersonic. It's going this direction. The flow is going that direction. And so it's going to have a shock wave going off the front. We might also realize it's probably going to have some expansion fans right here as the flow turns. And then finally at the back, it would have some more oblique shock waves. Okay, not too bad. But we still need to define a little bit more about it. So first off, just to make sure we understand this, I am going to tell you that this airfoil is a distance c, and it is a width t, and it is symmetric. So it means that each panel is the same length, and all the angles are the same. And I'll give that angle as that guy, epsilon. This is gonna drive me insane if I try to do it that way. I'm just gonna go with the E. There you go. Beautiful. Okay, so far, so good. Oh yeah, and all these lengths right here, I can call them L. Let's see here. That looks good. And we have some M1 that is going to be more than 1, because it's going supersonic. Now, let's define everything else we need to know. First off, we know that there's going to be a beta here. And we can also figure out a few values. First off, if I have P1 right here, after I go through a shock wave, P2 right here is going to be more than P1. We know that because we went through a shock wave. Behind that, I will have an expansion fan, so P3 is going to be less than P2 because that expansion fan decreased it. What happens in section 4 after that last oblique shock? Who cares? It's not attached to our, airfoil. So we really don't need to know anything about it. Now, if we used a similar process to our flat plate example, we can figure out the drag on this airfoil. Since it says 0 angle of attack right now, there is no lift because it is symmetric, but the drag would be, fairly similar. So how would we figure out the drag? Well, the drag is going to be equal to 2 times P2 times the length sine of the angle minus P3 times the length times sine of the angle. That looks good. Yep. And luckily for us, this L sine of the angle and L sine of the angle and that 2 help us out because we can figure out from trig, this right here is L over 2, this right here is L over 2, right? And this is the angle. Make sure I'm doing everything right here. Oh, that's not L over 2. My bad, sorry everybody. That is thickness over 2, and that is thickness over 2, and that is the length. So opposite over hypotenuse is sine. So what I get then is that sine of this guy is equal to T over 2 over L. Or if I rearrange that slightly and multiply, I can say that 2 times L times sine of this angle is equal to T. That's very helpful because that means that this guy right here is simply equal to P2 minus P3 times the thickness. So that is for 0 angle of attack. I can then, if I want to, put that in terms of a coefficient of drag, which is honestly much more important. And, a lot of interesting stuff can be done from this. However, this is at 0 angle of attack. And what I'm going to go through with you right now is I'm going to put it at a small angle of attack, like 5 degrees. And we're going to see how that changes everything. And we're also going to talk about some limiting cases here, because that angle of attack will alter how I solve this problem. Okay, So, with absolutely no further ado, let's begin. So I'm going to redraw this problem once again. Here's the center line. Here's my diamond wedge airfoil. Looks good. And this time, my airfoil is at an angle of attack. I'm going to draw this that looks nice. There we go. And I'm going to put that at an angle of attack of, we'll say 10 degrees. 10 degrees. Okay. Did I draw it at 10 degrees? No, I definitely did not. Okay, forgive me. I do my best here, but that's definitely not at 10 degrees. And so I've got the chord here, I've got the length here, and I've got the thickness right there, T. It's looking good. I'm liking it. Now we need a few other values. So I'm going to say that each of these angles is 5 degrees right here. And so when I look at this now, there's a lot of things I'm going to have to figure out. First off, I'm going to have to figure out what am I experiencing on the top right here. Is it going to be an expansion fan or a shock wave? I don't necessarily know. We're going to need to think about that. What am I experiencing on the bottom? Is that an expansion fan or a shock wave? I don't know yet. We're going to need to figure that out. And it's not horribly difficult to tell which one you're going to get, okay? So let's look at this right here. First off, angle of attack, that's equal to 10 degrees, okay? 10 degrees. So just if this was a flat plate right here, look at that chord line. My deflection for the bottom would be equal to 10 degrees, but that's compression. And my deflection for the top would also be equal to 10 degrees, but that would be expansion. Okay, so if it was a flat plate, I would have just an expansion fan on the top and just a shock wave on the bottom. But it's not a flat plate. So you see this right here, I've got this 5 degrees here and I've got this 5 degrees here. What does that do? Well, if you look at it, this 5 degrees on the bottom has increased my compression. And the 5 degrees on the top has decreased my expansion. That means that the deflection angle on the top and the bottom is different. I need to remember that. So my deflection angle for the bottom, for that shock wave which I'm going to experience, my deflection angle is going to be equal to 15 degrees. Okay? And my deflection angle at the top is going to be equal to 10 minus 5 degrees, which is simply equal to 5 degrees. And since I'm still having to go from the horizontal down 5 degrees, that would be an expansion fan. So I have an expansion fan on top, and I have a oblique shock on the bottom. A little bit messy right there. So let me see if I can clean that up a bit. Perfect, perfect. So you have to ask yourself, how is my flow being deflected? And if you're really getting confused, just pull it completely away from itself. Don't look at it as a full diamond wedge and just look at it as a side. So just to show that again, I'm going to look at this right here. This is side 2, and this one right here, I'll call this one, we'll call this one side 4. Because I'll make this one right here side 3, that one's right there side 5. So let's look at just side 2 again and get that idea again. So I'm making it into a flat plate, and I have to realize that, make sure I do this right here. Okay, so this one right here, this is just a flat plate, this is at 10 degrees. And this one right here is 5 degrees. So if I'm coming from the horizontal, I can figure out what this angle is. And that would have to be 5 degrees, okay? So that's my deflection angle. So this is the wedge's half angle right here. This is my angle of attack right here. And then from that, I can figure out my deflection angle. And you can see that my flow is having to be turned away from itself. It's expanding. So that's an important detail. That's going to happen anytime my angle of attack is actually higher than my deflection angle, or sorry, than my half angle. I'm going to get an expansion fan on the top. Okay, so with that, let's start working through this problem and figuring out the properties of each of these guys, because I now have a good idea what's going on here, and I believe I can solve for it. Okay. Hopefully you're ready. So I'm going to erase this guy, a little vision right here. If you didn't have it down yet, this is a video. You can go check it out later. And we'll get through it. I'm going to do the sections in order, so 2, 3, 4, and 2, 3, 4, and then 5. Actually, I'll do 2, 3, and 5 because all those are, no, 2, 3, 4, 5. Yeah, 2, 3, 4, 5. So first off, section 2. So now I need to give something else. I'm going to say that my Mach number here is going to be 2.0. Why 2.0? I like that as a Mach number. It works out well. And my pressure, we're just going to say that was equal to 1 atmosphere. Temperature, if we need it, is going to be equal to 288 Kelvin. Beautiful. Okay, so now for section 2. So, first off, section 2 is an expansion fan. So I'm going to use M1, which is equal to 2.0. I'm going to go over and find new one. I'm going to then add my deflection angle, which in this case is 5 degrees, because that's equal to my angle of attack minus the half angle. 10 minus 5 equals 5. And then from that, I'm going to get V2, and I'm going to head back and figure out my Mach 2, number 2. And then later on, if I want to, I can come back and get my properties. Mostly right now, I'm going to focus on getting those Mach numbers, at least for the expansion fans, because those are easiest. Okay, so let's do this. I've got a Mach number of 1. Mach number 1 is going to be equal to 2.0, so let's go to our Prandtl-Meyer function tables and figure things out from there. So I'm going over to the appendices, appendix C, there I am. I'm going to scroll down until I find a Mach number of 2.0, which I found right here. And that's got an angle of 26.38 degrees. We've seen that one before. How have we seen it before? Because we use the same number. So 26.38 degrees. Okay. So that's equal to 26.38. That means that my V2 is going to be equal to 31.38. And so now I have to jump back to those tables to actually get my second Mach number. So 31.73, that's close enough for me. That's a Mach number of 2.2. Okay. So this one right here is equal to 2.2. Now, in this case, we are going to need to keep all these Mach numbers because I have to care about the pressure on each panel to figure out the lift and the drag when I get to that point a little bit later from now. Okay? I have to know that. If I don't know that, all is lost and we're ruined and just everything's bad. We don't want that. So now I'm going to go to panel 3 and I have to figure out what is my deflection angle, which is honestly not that hard. So let's draw it. So I have just gone straight. So this is now panel 2 and I'm going down here. I know that these two lines are connected by 5 degrees. Make sure I do this right because I don't want to do it wrong. Yeah, that's looking pretty good. Okay. Perfect. So that one right there is 5 degrees. That's 5 degrees. That looks nice. Okay, so I want to find out what this angle is right here. And your first thought might be, it's going to be 5 degrees too. That would be what it was if I had it perfectly parallel to the chord line. But I don't have it perfectly parallel to the chord line. I do not at all. So erase from me. There we go. I'm going to have to figure out what that angle is, which isn't going to be too terrible. Okay, it's not going to be too terrible. At least I hope it's not. I'd really like for it not to be. Come on, let me make things simple on ourselves at least once. At least once. Okay, so let's do this. First off, this is an isosceles triangle. So I have 5 degrees here and 5 degrees here, which means that this guy right here is 170 degrees. Woo! Woo, that's a big angle. Because remember, there's 180 degrees in a triangle. And then I know that for a half circle, there's 180 degrees, which means that this guy right here has to be 10 degrees. So even though you probably thought your deflection angle was going to be another 5 degrees, it was actually 10. As a note, that is not like a coincidence. Aha, it's equal to the angle of attack. It is not equal to the angle of attack. It's equal actually to twice the half angle. Okay, that's where we're getting it from. So just don't get confused about that. It's because of that. So my flow, which was going along this one, is now going to turn. This is section 3 right here. And so I'm going to have theta 2, or I'll call this theta 3. I don't know. There's a lot of ways we can name these things. That's equal to 10 degrees, which means that V3 is going to be equal to 41.38. And so from that, I can get my final Mach number on the top, okay? On the top. So let's look it up. 41.38, ooh, pretty close. Mach number of 2.6, was that on purpose since that was very similar to the last problem? No, not at all, that was just by accident. But hey, happy accidents, I like it. Bob Ross was cool with it, I am too. Okay, so 2.6. So we've done the entire top right now, and we can go, and we will go to Appendix A to get all of our ratios for the pressures so we can solve everything else. Because you have to remember that P01 is going to be equal to P02, which is going to be equal to P03, because this is an isentropic flow across the top of my airfoil. It is not isentropic across the bottom because I'm going to hit a shock wave. And since I'm going to hit a shock wave, it's going to cause it to be very unhappy with us. So now let's focus in on the bottom, okay? So I did the top right here. Top. We'll come back to it later when we are ready to get all the pressures. But now let's just do the bottom. So I'm going to redraw the bottom just to make it easier on yourself as we work. There we go. I'm ignoring the top entirely, okay? Just does not exist right now. We can pretend like that is some sort of wall because we've already done all the math over there. This is section 4, that is section 5. And we're going to have a shock wave right here, and we'll figure out if we have an oblique expansion fan or a shock wave at that second section in a moment. Okay? Last thing here is that we have an angle of attack right here of 10 degrees, and I'm going to need to know that when I start figuring it out. And I have a flow over here that's M1 is equal to 2.0. So the first question is, what in the world is my deflection angle? Well, we worked it out earlier. It's 10 plus 5. That is my deflection angle. That is theta. I'm going to use that to find beta. Okay? So I'm going to have to go to my theta beta Mach diagram to do that. And I'm going to have a theta that's equal to 15 degrees and a Mach number that's equal to 2.0. And from that, I'm going to find out what my beta is. So give me a second and we'll get that ready. Okay, so now let me go ahead and paste this over here. Hopefully it works out properly. It did! Nice. I'll make that a bit bigger on us just to have it be a little bit easier. Okay, so we know our deflection angle. It's 2. Sorry, it's 15. I can't count. And we know what our Mach number is. So first thing we're going to do is, like I always do, I'm going to trace the Mach number line. So it's right here, this is 2.0. That's the one I have to care about, okay? And now I need to find that 15 degrees. So remember, each of these ones at the bottom is half a degree, so I need to go over 2 lines right here to get to 15 degrees. Oh, snap, that hit perfectly. Now I go over. Beautiful. And each of these is 1 degree. So that's 41, 42, 43, 44, 45 degrees. I'll have you know that's exactly what I was guessing it was going to be, because I picked out a hat, not because of some amazing engineering tradition. Okay, but beta is equal to 45 degrees. Great. We have our values. Let's keep on going. So from that diagram, we get that beta is equal to 45 degrees. Cool. Now, how are we going to solve this? Well, the same way we always do. First, we're going to find our normal Mach number, okay? Our normal Mach number. I'm getting out my calculator and getting it ready to go. I'm going to get distracted by cat videos this time. So first off, M1 normal is going to be equal to M1 sine of beta 1. Will there be a beta 2? I don't know. Probably not, but I'm going to just go on a limb here and say there could be. There totally could be. High enough angles of attack? You definitely could. So, yeah. So M1 sine of beta 1 is going to be equal to 2 sine of 45 degrees. Man, 45 degrees. 45 is one of those angles I love. It's like 30 degrees or something. That's a good one too. So 2 sine of 45. I should have known that one. Goodness. It's equal to 1.414. Okay. And now what do we do with that? Well, we're going to go to our not oblique shock tables, sorry. Our normal shock tables and find all of our properties. Normal shock tables. The biggest thing for us is we need to find first the pressure ratios, because we do need that, and then we're going to need to find the Mach number. So what I want to find P4 over P1. I also want to find P04 over P01. That's going to be very, very helpful. Though in the past that did give us bad numbers when we were using it. So I'm probably going to find, no, that's good. That P04, that ratio was fine. Yeah, that's a good one. And I also want to find what M4 normal. Sorry, my numbering here is killing me because I'm having to do it with 4s instead of like 2s. Okay, so let's go to our normal shock tables for Mach number of 1.4 and figure out what it is. Once again, I'm just going to the closest value because this is a very long problem and I do not want to have to continue to interpolate for each individual section. But I do want to show you every single step of the way how to solve this problem, minus the interpolation. So I'm going to go over to our appendices, Appendix B. There it is. I'm going to go down until I find a Mach number. That's the right one for me. And I've got it right here, 1.414. That's closer to this one, so I'll do 1.42 and call it good. So just so you know exactly where I am, I'm going to go ahead and screenshot this page after I remember which lines I needed. Okay, it is the 5th column. That's what I needed. There we go. So let's screenshot so you can see everything. Capture full page. Right here, that's my M1 normal. This is my pressure ratio, and this right here is the ratio of stagnation pressures, and this is my normal Mach number after the shock wave. Okay, so those are all the values I need. I'm going to write them on the next screen, so don't worry too much about writing them down right this second. And we'll go through the rest of this problem. So those numbers were, again, let's see, this was 2.186. This one was, let's see here, 0.954. And finally, 0.7314. I believe I was correct on that. I'm going to jump back real quick, just make sure I didn't, this one is up. I can't read my handwriting. That was 0.9531, not 0.954. Perfect. And just because well, you know that was for 1.42. So technically, it's not quite the right one. I would have to interpolate to get the correct one, or I could use, if you have a calculator, use the calculator to get the exact values for you really quickly. So with that, I need to find out what is M4 now. So M4 is going to be equal to M4 normal over sine of beta minus theta. So it's going to be equal to 0.7314 over sine of 45 minus 15. I am loving these numbers. Sine of 30, seriously? My goodness, that's just glorious. So that comes out to be 1.46. Well, I'll just say 1.46. I'm going to check that because I'm paranoid and making sure that I didn't make some horrible mistake. Nope, I did it right. 1.46. Okay. So we have our Mach number. We have the ratio of pressures, which we would need really badly for that. We have ratio of stagnation pressures. And so the last thing we're running into is that last section. So remember, we just did section 4. Now we have to do section 5. And so finally we get to answer the question, is that going to be a shock wave or an expansion fan? And it's got a really super easy answer. The answer is it's an expansion fan. How do I know that? I know that because the flow is already going this direction and it has to then turn and expand. It's turning away from itself, and so it's going to be an expansion fan right there. So let's do that very, very last section and we'll have it. I'm going to redraw it. I'm going to draw it straight because right now I don't really have to worry too much about what's going on there. Okay, here we are. I've got this guy. This is M4, and that's equal to 1.46. And then I have to figure out, once again, what is this deflection angle? Deflection angle 5, I guess? We got so many of these here. I want to then figure out what M5 is. So what is this deflection angle going to be? Well, let's do some math. So first off, if I'm doing it based on my shape right here, I've got 5 degrees for the half angle there and 5 degrees there, which makes this 170 because it's an isosceles triangle. And so that means that this angle right here is going to be 10 degrees. So theta 5 is equal to 10 degrees. Beyond that, everything is exactly the same for us. I can go ahead and do the problem just like I've done all the other Prandtl-Meyer sections in this problem. So let's figure that out and get it going. So I now need to go to Appendix C for a Mach number of 1.46, which hopefully will be in there. I don't know, but we'll pick something close. 1.46 is there. Happy days. Okay, so for 1.46, I have a Prandtl-Meyer function of 10.73 degrees. It's right there, not too bad. And we're going to do our major setup here. So this gives me V4, which is equal to 10.73 degrees. I'm then going to add theta, I guess 5 is what I called it, which is equal to 10 degrees. And then I get a value for theta, my Prandtl-Meyer function 5, which is equal to 20.73 degrees. And from that, I can then get what M5 is going to be equal to. Okay? What are you, M5? I don't know. We're going to find out in a second. So 20.73 degrees, what could it be? Scrolling down a bit. Oh my goodness, the numbers worked out exactly. 20.73 right here, which is a Mach number of 1.8. And for that one, beyond my other roundings, that was just serendipity there. So 1.8. Okay. So we have found the Mach number now on every single surface of our airfoil, okay? We found the Mach numbers on every single surface. So I'm going to redraw this guy over here to the side, and I'm going to show you what we have left to do. So right here, it's 1.46. Right here, it's 1.8. On the top two, I believe it was 2.2 and 2.6. I'm going to have to go back up there and find out. Yes, 2.2 and 2.6. And the last thing we're going to need to know here is that P4 over P1 is going to be equal to 2.186, and P04 over P01 is equal to 0.9531. There you go. Okay, so what we need to find now is we have to find out what is P2 over P1, what is P3 over P1, and what is P5 over P1. I need to know all those values. If I can find all those values, I'm golden. Okay, I can do so much. If I can't find the values, all is lost and just give up now. But the thing is, we can find all those values. It's not going to be that hard. So where are we going to find them? Well, we're going to do it along the top first. We need to remember that that was isentropic, okay? The second thing is that from here to here was also isentropic. So this actually makes it very, very simple for us, okay? So what do I mean by that? Well, I mean that first off, I know that P01 is equal to P02, which is equal to P03. I also know that P04 is equal to P05, but those are not equal to P01. Because I had that shock wave first, they're not the same thing. But that's enough information that I can go to my appendix and get all the values for 2.2, 2.6, 1.46, and 1.8, and figure out all these ratios. So let's go to the appendices now. I'll show that to you, and you'll be amazed and be like, wow, Dr. Kidd, you know so much stuff. And be like, I really do know a lot of stuff. And we'll just have a good time. So let's jump over there and get all the values. So here I am in my isentropic flow tables, and I have to do this for each of my sections. So I'm going to go on the top first. So that's Mach numbers of 2.2 and 2.6. Scrolling down here. Oh, sorry. What I need here is I need the ratio of stagnation pressure to actual pressure. That's all I care about right now. So this second column is where I need to get all my values from. Okay. So 2.2 way down here. Thank goodness they have it. And so that's going to be equal to 10.69. So P02 over P2 is 10.69. So let's write that down. P02 over P2 is equal to 10.69. Perfect. Okay? We got the first one. Now let's do P03. That's 2.6. We're going to get that value as well. So 2.6, go down a little bit right here, 2.6, and that's going to be 19.95. 19.95 right there, that's the ratio. Okay. And now we're going to get P04 over P4, which I'm not actually sure we'll really even need that one. So I'm going to leave that one alone. We'll get P05 over P5. There we go. This one we'll need. And that's going to be for a Mach number of 1.8. Yep. P05 over P5. That looks good. So Mach number of 1.8, let's go back a little bit. And that's right here. This is going to be 5.746 for that one right there. So now let's get our ratios. I want P2 over P1, P3 over P1, P4 over P1, which I already have, and P5 over P1. I need everything over my initial pressure. I need all of those. How do I get it? Well, it's not too hard. Let's do P2 over P1 first. So P2 over P1. I've done this in several problems, so you're going to probably be fairly familiar with where I'm getting this from. It's going to be equal to P2 over P02 times P01 over P1. Let's see here. Did I do it right? Yeah. Oh, but I don't have P01 over P1. I forgot to get it. Well, let's go ahead and get it. So one other value to grab. So P01 over P1, that's for a Mach number of 2. So Mach number 2 is right here. That would be 7.824, right there. That's the value I needed. Whoops, I forgot one, okay? Give me a break. Perfect. So P2 for P1 is going to be equal to the inverse of what I pulled out of the tables. So it's 1 over 10.69 times what I just got, which is P01 over P1, which is 7.824. And what's that equal? I don't know. Let's plug in my calculator. I got 0.732. Okay, that's good to know. That's the first one. And now let's figure out P3 over P1. Okay, so P3 over P1, it's isentropic, so I don't even have to worry about what P2 was. That's going to be equal to P3 over P03 times P01 over P1. And just remember that since it's isentropic, these two guys are equal. They're going to cancel, okay? That's why I'm not having to worry about them. So what's that equal to? That's going to be 1 over 19.95 times that 7.824 again. Okay, it's looking good. Let's plug it in my calculator and see what we get. Okay, so that's equal to 0.392. Okay, so we have the top now. Now let's do the bottom one. Now we already got P4 over P1. That's pretty easy. It was given earlier when we did this part right here. And we know what P04 over P01 is. So from that, we're going to have to go from there. Okay, so I want P5 over P1. That's the only one that's remaining. So I want to realize that, yeah, we'll do it that way. This will be equal to P5 over P05. That looks good. Times, yeah, we'll do it that way. P05 over P04. Looking good so far. And let's see here. Actually, I didn't need this one right here. My bad. Okay. And let's do it that way. Yes. Then I'm going to do P04 over P01. And then finally, P01 over P1. There we go. And remember that P05 and P04 are the exact same thing. Those cancel, and so I would have P5 over P1. Sometimes it takes a little bit of thought to figure out how you're getting these things, but it's not usually too terrible in the end. So I have all these values. So first off, P5 over P05 is the inverse of what I pull out of the table. So 1 over 0.5746. P04 over P01 I got from my normal shock tables, and that's equal to 0.9531. And finally, P01 over P1, that's another one we pulled out of the tables, and that is 7.824. Okay, so what's this come out to be? I don't know. Let's plug into our calculators and find out. I get it's equal to 1.298. Okay, so that is every single pressure ratio for this problem. Every single one. We did it. I'm loving it. It's looking pretty good. We're in a very good spot now to move on to the last little steps here. So remember, we have this guy at an angle of attack of 10 degrees. And I'm going to write down all the numbers we just got here to make sure I have them in place. So I have 0.732. I have 0.392. Then on the back here, let's see, I have 1.298. And P4 over P1 was 2.186. Okay, so we have all of those. We have our half angles of 5 degrees. We know that this right here is a length of L. This is a thickness T. This is a width C. And so from this, now we need to get our drag and our lift. Now, I showed you earlier how we get drag and lift. And so I'm going to go ahead and kind of do that now. So remember, this is section 2, section 3, section 4, section 5. Okay, so drag, I'm going to draw this out angle of attack here. It's going to be the force, the pressure going this direction. Okay, that's slowing it down, minus the pressure going in this direction. Okay, that's all I care about right now. And as a note, I'm going to do this. I'm going to just find, well, we'll call this the tangential force. Technically, this is like drag with zero angle attack, but I'm going to fix it later, and I'm going to have the normal component as well, okay? Those are not equal to lift and drag because it's at an angle of attack. I have to take that into account later, but it's a lot easier if I just pretend there's no angle of attack and then I correct it at the end. Okay, so I'm trying to figure out that T force, tangential, going tangent to our direction, or angle of attack, and then our normal force. It's going normal to it. Okay, so I have this section 2, that's going to, in section 4, that's going to be slowing it down. I have section 3 and section 5, that's going to be trying to speed it up, okay? That is my important thing here. I'm also doing this in prime thing, so it's always per unit span. And so I'm trying to figure out my area. It's not honestly that hard. Like my area here is just T over 2 times the length, which is 1, okay? That's all it is. So let's do that. So make sure I do this right. T prime is going to be equal to, yeah, do this right. Pressure 1 times, I have to multiply everything by the pressure just to get it in terms that make sense. And let's make sure I do all this right. Yep. Pressure 1 times T over 2. That's the same for all of them. And that's going to be simply equal to P2 over P1 plus P4 over P1 minus P3 over P1 minus P5 over P1. Okay, so the two on the back are trying to speed it up, so they're not drag force, and the two in the front are trying to slow it down. Okay, so I got that. That's looking pretty dang good. Nice. Now let's find N prime, okay? Let's find this N prime, and we can go from there. Now, if I'm redrawing this again for N prime, once again, I'm only caring about forces that are going like this, okay? All that stuff right here. Yes, yes. That should do it just fine. Okay. And what I can realize then is that my area, because pressure is equal to force over area, my area in this case is going to be equal to C over 2 times 1. Why C over 2? Because technically it's at an angle. I would need to figure out the component that's going perpendicular in this direction. And so that would just end up being C over 2. Makes it really simple to me. I like it. So doing it again, very, very similar. I have 2 and 3, which are trying to push it down. And I have 4 and 5, which are trying to push it up. So I'm trying to do lift. So 4 and 5 are going to be positive because they're pushing up. And 2 and 3 are going to be negative because they're trying to push it down. So it'll be equal to P1 times C over 2. And now I work all the ratios. So I have P4 over P1 plus P5 over P1 minus P2 over P1. There you go. Minus P3 over P1. That looks correct. And notice that those are not the same thing. Okay. So we're getting to our last little step here. And I'm probably going to leave some of this to let you mess around with because I'm running low on time here. But I have now this shape, and I have found a resultant force. Okay, I found a resultant force. Gotta make sure I draw this correctly. Yeah. I'm going to call that R. So it has the component N prime as I wrote it, and it has this component T prime. But you realize that is not the same as lift. It's not, okay? That's not the same as lift. Not the same thing. I have to correct it, okay? I have to correct it, otherwise all is lost. So how do I correct it? Hard, painstaking effort. Okay? Yeah, there's no jumping around that too terribly much. But it's not horrible. You have to do that a lot with this. So let's get into that real quick. Now, if you remember, I probably should have written these slightly differently. All the way back in aerodynamics 1, we had an equation that said that lift is equal to my normal force cosine of alpha minus my axial force sine of alpha. So sorry, I called it tangential. I should have called it axial. Sue me. And don't sue me, please. Don't have the time. Normal force sine of alpha plus my axial force cosine of alpha. So if I want to find the lift and drag, I can then just put these into this equation where I have my N prime right there and I have A right there. Now I'm not going to bother to do this right now. You could also go to coefficient of lift and coefficient of drag without too much terrible, painful work, and you would have your final answer. But here you go. I've walked through most of a diamond wedge example. If you do get stuck on going from the axial, sorry, I should call that axial, and normal components to the lift and drag, please let me know and I can always add more. Cool. That'll be it for today. Bye.